The Earth is the home of all known life. Every plant, animal, ocean, mountain, and human exists on this small planet orbiting a medium-sized star in a vast universe. Understanding how the Earth formed helps us understand not only our planet, but also the processes that shape all planets in the universe. The story of Earth's formation is a story that begins long before the Earth itself existed. It begins with the birth of the universe, the creation of matter, the formation of stars, and the slow organization of dust and gas into planets. This story is based on evidence from physics, chemistry, geology, astronomy, and biology. Scientists use observations, experiments, and mathematical models to reconstruct this history. This text explains the formation of the Earth in simple, clear, scientific language. It avoids unnecessary technical terms and explains important ideas step by step. Scientists believe that the universe began about 13.8 billion years ago in a state that was extremely hot and extremely dense. At that time, all matter and energy were concentrated in a very small region. Then, space itself began to expand. This event is called the Big Bang. The Big Bang was not an explosion that happened at one point in space. It was an expansion of space everywhere at once. As space expanded, it cooled. As it cooled, different forms of matter became possible. In the first tiny fractions of a second, the universe contained only energy and basic particles. Later, these particles formed protons and neutrons. After a few minutes, protons and neutrons combined to form the nuclei of simple atoms. After about 380,000 years, the universe had cooled enough for electrons to join these nuclei and form full atoms. At this point, light could travel freely through space. This is why we can still observe the early universe today through cosmic background radiation. The first elements that formed were hydrogen and helium. About 75% of the normal matter in the universe became hydrogen, and about 25% became helium. Very small amounts of lithium were also formed. Heavier elements such as carbon, oxygen, nitrogen, silicon, and iron did not exist yet. These elements would be created later inside stars. Hydrogen atoms consist of one proton and one electron. Helium atoms consist of two protons, two neutrons, and two electrons. These simple atoms became the raw material for the first stars. After the first atoms formed, the universe entered a period sometimes called the Dark Ages. There were no stars yet, and no light sources except the weak glow of background radiation. Over millions of years, gravity slowly pulled slightly denser regions of gas together. These regions grew larger and denser. Eventually, their centers became hot enough for nuclear fusion to begin. When hydrogen nuclei begin to fuse into helium, energy is released. This energy creates light and heat. At this moment, a star is born. The first stars were very large and very bright. They lived short lives and ended in powerful explosions called supernovae. Inside stars, nuclear fusion creates new elements. In smaller stars like the Sun, hydrogen is converted into helium. In larger stars, helium can be converted into carbon and oxygen. Even heavier elements are created in massive stars. When a massive star explodes as a supernova, it releases huge amounts of energy. This energy allows atoms to capture particles and form very heavy elements such as gold, uranium, and lead. These explosions spread newly formed elements into space. The gas and dust enriched with heavy elements become part of new stars and planetary systems. All the elements found on Earth were created in earlier generations of stars. In this sense, every atom in your body was once inside a star. About 4.6 billion years ago, a cloud of gas and dust in one part of the Milky Way galaxy began to collapse under gravity. This cloud was enriched with heavy elements from earlier supernova explosions. As the cloud collapsed, it began to spin. Most of the mass moved toward the center, where it formed the sun. The remaining material formed a flat, rotating disk around the sun. This disk is called a protoplanetary disk. Within this disk, dust particles collided and stuck together. Over time, these particles formed larger and larger bodies. Tiny dust grains collided and formed small clumps. These clumps became kilometer-sized objects called planetesimals. Planetesimals collided and merged to form even larger bodies called protoplanets. Gravity played a key role in this process. As objects became larger, their gravity became stronger, allowing them to attract even more material. This process took millions of years and resulted in the formation of the planets. Close to the sun, temperatures were very high. Light gases such as hydrogen and helium could not remain in this region. They were pushed away by the solar wind. Only heavy materials such as rock and metal could remain. This is why the inner planets, Mercury, Venus, Earth, and Mars, are rocky. Farther from the sun, temperatures were lower. In these regions, gases and ice could remain, allowing gas giants and ice giants to form. The Earth formed at a distance from the sun where temperatures were suitable for liquid water to exist. This region is often called the habitable zone. If the Earth had formed slightly closer to the sun, its water would have evaporated. If it had formed slightly farther away, its water would have frozen. This special position allowed the Earth to develop oceans, an atmosphere, and eventually life. When the Earth first formed, it was very different from the planet we know today. It was extremely hot, with a surface covered in molten rock. There were no oceans, no atmosphere as we know it, and no life. The young Earth experienced constant impacts from asteroids and other planetary debris. These collisions released huge amounts of energy and kept the planet hot. Another important source of heat was radioactive decay. Certain unstable elements inside the Earth released energy as they slowly changed into more stable forms. This internal heat still exists today and drives many geological processes. As the Earth heated up, its materials began to separate by density. Heavy elements, such as iron and nickel, sank toward the center, while lighter materials rose toward the surface. This process is called differentiation. It created the main layers of the Earth: the core, rich in iron and nickel; the mantle, made of hot, dense rock; the crust, made of lighter rock. The formation of the core released even more heat and helped create Earth's magnetic field. The Earth's outer core is made of liquid iron and nickel. As this liquid moves, it generates electric currents. These currents create a magnetic field around the Earth. This magnetic field is very important because it protects the Earth from harmful solar radiation. Without it, the solar wind could slowly remove the atmosphere and damage life on the surface. One of the most dramatic events in Earth's history was the formation of the Moon. Scientists believe that a Mars-sized object collided with the young Earth about 4.5 billion years ago. This collision released a large amount of material into space. Over time, this material came together to form the Moon. This idea is known as the giant impact hypothesis. The Moon has had a strong influence on Earth. It stabilizes Earth's rotation, creates ocean tides, and may have helped make the climate more stable. The Earth's first atmosphere was made mostly of hydrogen and helium, but this atmosphere was lost to space because Earth's gravity was not strong enough to hold these light gases. Later, volcanic eruptions released gases from inside the Earth. These gases formed a second atmosphere, made mainly of water vapor, carbon dioxide, nitrogen, and small amounts of other gases. This atmosphere was very different from the one we have today. There was almost no oxygen. As the Earth slowly cooled, water vapor in the atmosphere condensed into liquid water. Rain fell continuously for millions of years. This long period of rainfall filled low areas of the surface and created the first oceans. Additional water may have arrived from comets and icy asteroids that collided with the Earth. The early oceans were rich in chemical compounds. Energy from lightning, ultraviolet radiation, and volcanic heat drove chemical reactions in the water. Simple molecules combined to form more complex organic molecules, such as amino acids and simple sugars. These molecules are the basic building blocks of life. At some point, certain chemical systems became able to copy themselves. This was a key step in the origin of life. Scientists do not yet know exactly how life began, but they agree that it started through natural chemical processes. The first life forms were simple single-celled organisms. They lived in the oceans and obtained energy from chemical reactions or sunlight. Some early organisms developed the ability to use sunlight to produce energy. This process is called photosynthesis. Photosynthesis uses carbon dioxide and water to produce organic matter and releases oxygen as a waste product. Over millions of years, oxygen slowly accumulated in the atmosphere. This event is called the Great Oxygenation Event. Oxygen is very reactive. As it accumulated, it changed the chemistry of the oceans and the atmosphere. It allowed new forms of metabolism to evolve and eventually made complex life possible. It also led to the formation of the ozone layer, which protects the surface from harmful ultraviolet radiation. By this point, the Earth had oceans, an atmosphere, a magnetic field, and a stable climate. These conditions made it possible for life to develop and spread. Life began to influence the planet in return, changing the atmosphere, the surface, and even the climate. The Earth and life evolved together. The history of the Earth is extremely long. It covers about 4.6 billion years. To understand this vast time scale, Scientists divide Earth's history into large sections called eons, eras, periods, and epochs. These divisions are based on major changes in Earth's geology, climate, and life. The main eons are Hadean, Archean, Proterozoic, Phanerozoic. Each eon represents a very different stage in Earth's development. The Hadean eon covers the first 500 million years of Earth's history. During this time, the Earth was extremely hot and experienced constant impacts. There were no stable oceans or continents at first. Over time, the surface cooled enough for solid rock and liquid water to exist. The name Hadean comes from Hades, the ancient Greek underworld, because of the extreme conditions. The Archean eon began about 4 billion years ago. During this time, the first stable continents formed and the first life appeared. Life was simple and microscopic. It consisted mainly of bacteria and similar organisms. These early life forms played a crucial role in changing the atmosphere and oceans. The Proterozoic eon saw the rise of oxygen in the atmosphere and the appearance of more complex cells. Some organisms developed nuclei and other internal structures. These are called eukaryotic cells. Later in this eon, the first multicellular organisms appeared. The Phanerozoic eon began about 540 million years ago and continues to the present. It is divided into 3 eras: Paleozoic, Mesozoic, Cenozoic. This is the time when complex plants and animals became common and left abundant fossils. The Earth's crust is broken into large pieces called tectonic plates. These plates float on the hot, slowly moving mantle beneath them. Plate tectonics causes continents to move, oceans to open and close, mountains to rise, and earthquakes and volcanoes to occur. This process has been active for most of Earth's history and has greatly influenced climate and life. At several times in Earth's history, most of the continents were joined together into a single large landmass called a supercontinent. The most famous supercontinent is Pangaea, which existed about 300 million years ago. Supercontinents eventually break apart due to tectonic forces, and the cycle repeats over hundreds of millions of years. Earth's climate has changed many times. There have been long warm periods and long ice ages. These changes were caused by factors such as volcanic activity, changes in atmospheric gases, the movement of continents, and variations in Earth's orbit. Climate changes strongly influence the evolution and extinction of life. Several times in Earth's history, large numbers of species disappeared in relatively short periods. These events are called mass extinctions. They were caused by factors such as asteroid impacts, massive volcanic eruptions, and rapid climate change. Mass extinctions are destructive, but they also create opportunities for new forms of life to evolve. Life does not only adapt to the planet, it also changes it. Plants and microorganisms change the composition of the atmosphere. Roots break rocks and create soil. Reefs change ocean currents. The Earth today is very different from the Earth without life. The surface of the Earth is divided into continents and oceans. This structure did not exist in the early history of the planet. Continents formed slowly as lighter rocks accumulated and became stable over long periods of time. Ocean basins formed where the Earth's crust was thinner and denser. Water collected in these low areas, creating the oceans. Today, oceans cover about 70% of the Earth's surface and play a major role in regulating climate. Rocks on Earth are constantly changing through a process known as the rock cycle. There are three main types of rocks. Igneous rocks, formed from molten magma sedimentary rocks. Formed from layers of sediment, metamorphic rocks, changed by heat and pressure. This cycle shows that Earth is an active and changing planet. Volcanoes release material from inside the Earth to the surface. This includes lava, gases, and ash. Volcanic activity helped form the early atmosphere and oceans. It also created new land and provided minerals essential for life. Although volcanic eruptions can be destructive, they are a natural part of Earth's processes. Earthquakes occur when tectonic plates move suddenly. Most earthquakes happen at plate boundaries. These movements release energy stored in rocks. Earthquakes reshape the surface and remind us that Earth is constantly in motion. Mountains form when tectonic plates collide or when magma rises from below. Over time, erosion by wind, water, and ice wears mountains down. This material is transported and deposited elsewhere. Erosion and mountain building are part of a balance that shapes the landscape. Earth's atmosphere regulates temperature by trapping heat. This process is called the greenhouse effect. Without this natural effect, Earth would be too cold for life. Gases such as carbon dioxide, water vapor, and methane play key roles in this system. Carbon moves between the atmosphere, oceans, land, and living organisms. Plants absorb carbon dioxide during photosynthesis. Animals release carbon dioxide through respiration. Over long time scales, carbon is stored in rocks and fossil fuels. Water continuously moves between the oceans, atmosphere, and land. Evaporation, condensation, precipitation, and runoff are key processes in the water cycle. This cycle distributes heat and supports life. Oceans absorb heat and carbon dioxide from the atmosphere. Ocean currents move heat around the planet, influencing climate patterns. Without oceans, Earth's climate would be much more extreme. The Earth operates as a complex system where geology, atmosphere, oceans, and life interact. Changes in one part of the system affect other parts. This balance has allowed Earth to remain habitable for billions of years. The sun is the main source of energy for the Earth. Almost all natural processes on the surface depend on sunlight. Solar energy drives weather, climate, ocean currents, and photosynthesis. Changes in solar output can influence Earth's climate over long periods. Earth orbits the sun in a nearly circular path. The shape of this orbit changes slightly over long timescales. Earth's axis is tilted about 23.5 degrees. This tilt causes the seasons. Variations in orbit and tilt contribute to climate cycles known as Milankovitch cycles. Because of Earth's tilt, different parts of the planet receive different amounts of sunlight during the year. When the northern hemisphere is tilted toward the sun, it experiences summer. When tilted away, it experiences winter. This pattern affects ecosystems and climate. The moon helps stabilize Earth's rotation and tilt. Without the moon, Earth's tilt might change more chaotically, leading to extreme climate variations. This stability has helped life evolve under relatively steady conditions. Earth still contains heat from its formation and from radioactive decay. This heat drives mantle convection, plate tectonics, and volcanic activity. Without internal heat, Earth would be geologically dead like the moon. Minerals provide the raw materials for life and technology. They also influence chemical reactions in soils and oceans. The variety of minerals on Earth is one reason for the diversity of life. Soil forms when rocks are broken down by weathering and combined with organic material. Soil is essential for plant growth and land ecosystems. The development of soils was a key step in the colonization of land by life. The biosphere includes all regions where life exists. Life has been found deep underground, in the deep ocean, and in extreme environments. This shows the adaptability of life. Feedback loops occur when a change in one system affects another system, which then influences the first system. Some feedbacks stabilize the climate, while others amplify changes. Understanding these loops is important for understanding climate change. Over long time scales, Earth tends to regulate its temperature and chemistry. This idea is sometimes called the Gaia hypothesis, although it is debated. The interaction between geology, atmosphere, oceans, and life creates long-term stability. In the early history of the Earth, the sun was weaker than it is today. Despite this, the Earth was warm enough to support liquid water. This is known as the faint young sun paradox. It is explained by higher concentrations of greenhouse gases in the early atmosphere. These gases trapped more heat and kept the planet warm. At several times in Earth's history, the planet may have been almost completely covered by ice. These periods are called snowball Earth events. They were likely caused by changes in atmospheric gases and continental positions. Volcanic activity eventually released enough carbon dioxide to warm the planet again. The composition of Earth's atmosphere has changed many times. Early atmosphere, water vapor, carbon dioxide, nitrogen. Later, increasing oxygen, modern nitrogen, oxygen, argon, and trace gases. These changes were driven by volcanic activity, chemical reactions, and life. As oxygen increased, some of it formed ozone in the upper atmosphere. The ozone layer absorbs harmful ultraviolet radiation. This allowed life to safely move on to land. Over time, ecosystems became more complex. Food webs formed, with producers, consumers, and decomposers. These systems recycle nutrients and energy. Predation drove rapid evolutionary change. Prey evolved defenses. Predators evolved better hunting strategies. This evolutionary arms race increased diversity. Life adapted to extreme conditions such as high heat, high pressure, acidity, and salinity. These organisms are called extremophiles. Their existence expands our understanding of where life can exist. Biodiversity increases ecosystem stability and resilience. Diverse systems are better able to recover from disturbances. Loss of biodiversity can weaken ecosystems. Over millions of years, carbon dioxide is regulated by the balance between volcanic release and rock weathering. This balance helps stabilize Earth's climate. Disrupting this balance can lead to climate change. With the rise of agriculture and industry, humans began to significantly influence Earth's systems. Deforestation, fossil fuel use, and pollution altered the atmosphere and ecosystems. Humans became a geological force. The Industrial Revolution marked a major turning point. Human use of fossil fuels increased rapidly. Carbon dioxide levels in the atmosphere began to rise much faster than in natural cycles. Modern climate change is driven mainly by increased greenhouse gas emissions. This leads to rising global temperatures, melting ice, and changing weather patterns. These changes affect ecosystems, sea levels, and human societies. The Earth system responds to changes through feedbacks. Some feedbacks increase warming, such as ice melting, while others reduce it, such as plant growth. Understanding these responses is important for predicting the future. Oceans absorb much of the excess heat and carbon dioxide. This leads to ocean warming and acidification. These changes affect marine life and food chains. The cryosphere includes glaciers, ice sheets, and sea ice. Melting ice contributes to sea level rise. Ice loss also reduces Earth's reflectivity, increasing warming. Rapid environmental changes stress ecosystems. Species must adapt, migrate, or face extinction. Human actions influence which species survive. The future depends on human choices. Reducing emissions, protecting ecosystems, and managing resources can limit change. Earth's systems will continue to evolve. Even if humans disappear, Earth will continue to change. Mountains will erode, continents will move, and life will evolve. The planet's story is much longer than human history. Earth's history shows that change is constant. Life has survived many crises, but not without loss. Understanding the past helps guide future decisions. Humans now influence Earth systems at a planetary scale. This creates responsibility to act wisely. Science provides knowledge, but action requires choices. The Earth is one of billions of planets in the Milky Way galaxy and trillions in the observable universe. Studying Earth's formation helps scientists understand how planets form elsewhere and whether life might exist on other worlds. Discoveries of exoplanets show that planetary systems are common. Earth is unique in our solar system because of its stable climate, liquid water, and active geology. Mars lost much of its atmosphere and water. Venus experienced runaway greenhouse warming. These comparisons show how small differences can lead to very different outcomes. Scientists search for life on Mars, icy moons like Europa, and distant exoplanets. They look for signs such as water, organic molecules, and atmospheric gases. Understanding Earth's origin helps guide this search. Many details about Earth's formation and the origin of life are still unknown. Science continues to improve through new observations, experiments, and theories. Uncertainty is a natural part of scientific progress. Satellites, deep-sea probes, and supercomputers allow scientists to study Earth in new ways. These tools improve climate models, geological maps, and planetary exploration. Technology expands our understanding of Earth. Understanding Earth's history helps people appreciate the planet's complexity and fragility. Education supports informed decisions and responsible behavior. Knowledge connects humanity to the larger story of the universe. Human lives are short compared to geological time. Mountains rise and fall, oceans open and close, and species appear and disappear. This long perspective encourages humility and care. Earth's story is not finished. New changes will occur, new species will evolve, and new climates will form. The planet remains dynamic. The Earth formed through a long sequence of physical, chemical, and biological processes. From the birth of the universe to the rise of life and civilization, Earth is a product of natural laws and chance events. Understanding this story helps us understand ourselves. The formation of the Earth is a story of transformation. From simple particles to complex systems, from dust to oceans and forests, the Earth became a living world. This knowledge gives meaning to our place in the universe and reminds us of our responsibility to protect our planet. Our Earth is often described as a stable and familiar planet, but beneath this apparent stability lies a complex system of subtle motions, slow transformations, and hidden physical processes. Many of these processes operate on timescales far beyond human perception, shaping the planet quietly over millions or even billions of years. One of the less obvious features of Earth is that it is not a rigid object. The solid surface floats on a slowly moving mantle, and even this mantle is not static. It flows very slowly, similar to extremely thick honey, transferring heat from the deep interior toward the surface. This slow motion drives the long-term movement of continents, the opening and closing of oceans, and the rise and fall of mountain ranges. Earth's rotation itself is not perfectly constant. The length of a day slowly increases over time due to the gravitational interaction with the moon. The moon raises tides in Earth's oceans, and the friction from these tides gradually slows Earth's spin. Hundreds of millions of years ago, a day on Earth lasted only about 22 hours. In the distant future, days will be longer than 24 hours. The planet also experiences a slow wobble in its axis called axial precession. This wobble completes a cycle roughly every 26,000 years and causes the position of the seasons relative to Earth's orbit to shift slowly over time. This motion influences long-term climate patterns and contributes to cycles of ice ages and warm periods. Earth is surrounded by invisible but important fields. One of them is its gravitational field, which is not uniform across the surface. Variations in rock density, mountain ranges, ocean trenches, and mantle structures cause gravity to be slightly stronger in some places and slightly weaker in others. Modern satellites map these variations and help scientists understand the structure of Earth's interior. Another invisible system is Earth's magnetic field. Generated by the movement of liquid iron in the outer core, this field forms a protective bubble called the magnetosphere. It deflects charged particles from the sun and prevents much of the atmosphere from being stripped away into space. Without this magnetic shield, Earth might resemble Mars, which lost much of its atmosphere after its magnetic field weakened. The atmosphere itself is not just a passive layer of gas. It is an active chemical and physical system. Tiny particles called aerosols float in the air and influence cloud formation, sunlight reflection, and even rainfall patterns. Some aerosols come from natural sources such as volcanoes, deserts, and oceans, while others come from human activity. Water on Earth is also part of a much deeper system than the visible oceans, lakes, and rivers. Huge amounts of water are stored underground in aquifers, deep rock layers, and even inside minerals in the mantle. Some water molecules are carried down into the mantle by subducting tectonic plates and may remain there for hundreds of millions of years before returning to the surface through volcanic eruptions. Earth's surface is constantly being reshaped by erosion. Wind, rain, ice, and temperature changes slowly break down rocks into smaller particles. These particles are transported by rivers, glaciers, and ocean currents and eventually deposited elsewhere. Over long periods, entire mountain ranges can be worn down and their material spread across plains and ocean basins. Life itself is a geological force. Plants accelerate rock weathering by producing acids in their roots. Microorganisms alter minerals through chemical reactions. Coral reefs build massive limestone structures visible from space. Over time, living organisms reshape the surface, the atmosphere, and even the chemistry of the oceans. The oceans play a crucial role in stabilizing Earth's climate. They absorb vast amounts of heat and carbon dioxide, reducing temperature extremes. Ocean currents redistribute heat from the equator toward the poles, making Earth more habitable than it would otherwise be. Changes in ocean circulation have caused major climate shifts in the past and may do so again in the future. Earth also interacts continuously with space. Tiny particles from comets and asteroids fall into the atmosphere every day. Solar radiation and solar storms affect the upper atmosphere and magnetic field. Even distant gravitational influences from other planets slightly modify Earth's orbit over long periods. Perhaps the most remarkable feature of Earth is that all of these physical, chemical, and biological processes are connected. Changes in one system affect the others. A shift in climate alters vegetation. Vegetation changes affect atmospheric gases. Atmospheric changes influence temperature, which affects ice, oceans, and erosion. The planet functions as an integrated system rather than a collection of separate parts. Earth is therefore not just a planet with rocks, air, and water. It is a dynamic, self-modifying system that has evolved over billions of years and continues to change today. Understanding these subtle processes helps us appreciate both the stability that allows life to exist and the slow forces that will continue to reshape the planet long after human civilization has changed or disappeared. The Earth appears calm and unchanging when observed over a human lifetime, yet on geological timescales, it is a restless and evolving body. The solid ground beneath our feet is only the thin outer skin of a planet whose interior remains extremely active. Beneath the crust lies the mantle, a vast region of hot rock that slowly circulates over millions of years. This slow circulation transfers heat from the deep interior toward the surface and acts as the engine of plate tectonics. Continents drift, collide, and separate because of this hidden motion, and the pattern of oceans and land is therefore temporary rather than permanent. The boundaries between tectonic plates are zones of intense geological activity, where plates pull apart, magma rises and creates new crust. Where plates collide, mountains grow and earthquakes release accumulated stress. Where one plate sinks beneath another, deep ocean trenches form and water is carried into the mantle. This water lowers the melting temperature of rocks and helps fuel volcanic activity. In this way, surface water becomes part of deep earth processes and later returns to the surface through eruptions, completing a slow but powerful cycle. Earth's interior is also the source of its magnetic field. The liquid iron in the outer core moves in complex patterns driven by heat and rotation. These movements generate electric currents, and the currents create the magnetic field. This field extends far into space and forms a protective region that shields the atmosphere from much of the solar wind. Without this protection, charged particles from the sun would gradually erode the atmosphere and expose the surface to harmful radiation. The magnetic field is therefore one of the invisible conditions that make long-term habitability possible. The shape of Earth itself is a product of motion. The planet is slightly flattened at the poles and bulges at the equator because of its rotation. This shape influences ocean circulation, atmospheric movement, and even the distribution of gravity. Gravity is not exactly the same everywhere. It varies slightly due to differences in mass within the planet. Mountains, dense rock formations, and deep mantle structures all affect the local gravitational field. By measuring these variations, scientists can infer what lies beneath the surface without directly drilling into it. Earth is also constantly exchanging matter and energy with its surroundings. Each year, thousands of tons of cosmic dust fall into the atmosphere, adding a small but continuous input of material from space. At the same time, light gases slowly escape from the upper atmosphere into space, especially during periods of high solar activity. Over billions of years, this slow loss and gain of material has slightly changed the planet's composition. The atmosphere is far more than a passive layer of air. It is a dynamic system with complex circulation patterns that redistribute heat and moisture. Warm air rises near the equator, flows toward higher latitudes, cools and sinks, creating large-scale wind cells. These winds drive ocean currents, shape weather systems, and transport dust, pollen, and nutrients across continents and oceans. The atmosphere also plays a chemical role, breaking down pollutants, forming clouds, and regulating the amount of sunlight that reaches the surface. Clouds are especially important regulators of Earth's energy balance. They reflect some sunlight back into space, cooling the planet, but they also trap infrared radiation, warming it. The net effect depends on cloud type, height, and location. Small changes in cloud behavior can therefore produce significant climate effects, making clouds one of the largest uncertainties in climate prediction. Water on Earth exists in many hidden forms. Beyond the visible oceans and rivers, enormous quantities of water are stored underground in porous rocks and sediments. Even deeper, water is trapped within the crystal structures of minerals in the mantle. This internal water influences how rocks melt, how plates move, and how volcanoes behave. Earth may contain as much water inside its interior as on its surface, locked away in forms that are invisible but geologically powerful. Life interacts with all these systems. Through photosynthesis, plants remove carbon dioxide from the atmosphere and release oxygen. Through respiration and decay, organisms return carbon to the air and soil. Over time, this biological cycling has transformed the atmosphere from one dominated by carbon dioxide into one rich in oxygen. This transformation made complex life possible, but also tied life's future to the stability of climate and chemistry. The oceans act as both a buffer and a memory for climate. They absorb heat during warm periods and release it during cooler times. They also store vast amounts of carbon, which can be released or absorbed depending on temperature, circulation, and biological activity. Changes in ocean circulation have caused abrupt climate shifts in the past, such as the sudden cooling events associated with melting ice sheets. The oceans therefore link short-term weather to long-term climate history. Perhaps the most striking feature of Earth is that none of its major systems operate in isolation. The interior influences the surface. The surface affects the atmosphere shapes the climate controls life, and life modifies the surface and atmosphere in return. Earth is a network of feedbacks rather than a simple machine. Stability emerges not from stillness, but from continuous adjustment. This interconnectedness means that small changes can have large consequences over long times. A slight shift in orbital shape can trigger an ice age. A gradual increase in greenhouse gases can alter global temperatures. A slow rearrangement of continents can change ocean currents and transform ecosystems. Earth's history is therefore not a straight line, but a complex pattern of interactions, adjustments, and transformations. Understanding the Earth requires thinking across many scales of time and space. It requires seeing mountains not as permanent objects, but as temporary features in a long cycle of uplift and erosion. It requires seeing oceans not as static bodies of water, but as moving, breathing systems that exchange heat and chemicals with the atmosphere and the deep earth. It requires seeing life not as separate from geology, but as one of its active components. Earth is not only a place where life exists, it is a planet that has been shaped by life and continues to be reshaped by it. The story of Earth is therefore not just a story of rocks and physics, but also a story of living processes woven into the fabric of the planet itself. While Earth's surface is shaped by slow geological forces, it is also constantly modified by faster processes such as weather, erosion, and biological activity. Rain dissolves minerals from rocks, wind transports fine particles across continents, and glaciers carve valleys and move vast amounts of sediment. These processes reshape landscapes on timescales of thousands to millions of years, gradually transforming mountains into plains and carrying their material into the oceans. Rivers play a particularly important role in this transformation. They act as conveyors of both matter and energy, transporting sediments, nutrients, and organic material from land to sea. Along their paths, rivers create fertile floodplains and deltas that support dense ecosystems and human societies. Over time, rivers shift their courses, abandon old channels, and create new ones, constantly rewriting the geography of the land. The oceans are not uniform bodies of water, but layered and structured systems. Temperature, salinity, and pressure vary with depth and location, creating distinct water masses that circulate globally. This circulation connects the polar regions to the tropics and the surface to the deep sea. Cold, dense water sinks near the poles and flows along the ocean floor toward lower latitudes, while warmer surface water moves poleward. This slow global circulation, sometimes called the ocean conveyor, redistributes heat and influences climate patterns over centuries. The chemistry of the oceans is also dynamic. Seawater contains dissolved gases, salts, nutrients, and trace metals that are constantly exchanged with the atmosphere, the seafloor, and living organisms. Marine life removes carbon, nitrogen, and phosphorus from the water and returns them through decay and sedimentation. Over long periods, some of this material becomes buried in sediments and eventually forms rocks such as limestone and shale. These rocks later return their elements to the surface through uplift and erosion, closing another slow cycle. Earth's climate system is driven by energy from the sun, but it is regulated by feedbacks within the planet. Ice reflects sunlight, cooling the surface, while dark surfaces, such as forests and oceans, absorb sunlight and warm it. Water vapor amplifies warming by trapping heat, while clouds can both warm and cool depending on their type. These feedbacks can stabilize climate or push it toward new states, such as ice ages or warm greenhouse periods. Volcanic eruptions connect Earth's interior to its atmosphere. They release gases such as carbon dioxide, sulfur dioxide, and water vapor that influence climate and atmospheric chemistry. Large volcanic events in the past have caused temporary cooling by injecting reflective particles into the atmosphere, while sustained volcanic activity has contributed to long-term warming by increasing greenhouse gas levels. Thus, even processes deep within the planet can shape surface conditions. Earth's orbit around the sun is not perfectly constant. It changes slowly due to gravitational interactions with other planets. The shape of the orbit, the tilt of Earth's axis, and the timing of the seasons all vary in predictable cycles. These variations influence how sunlight is distributed across the planet and are linked to the timing of ice ages. Climate is therefore influenced not only by internal processes, but also by the broader dynamics of the solar system. The biosphere responds to climate change, but also modifies it. As temperatures shift, species migrate, adapt, or disappear. Vegetation patterns change, altering how much sunlight the surface absorbs and how much carbon is stored in plants and soils. The spread of forests after the last ice age, for example, changed regional climates by increasing moisture recycling and reducing surface reflectivity. In this way, life acts as both a responder and a driver of environmental change. Soils form the thin living skin of the continents and are essential for terrestrial ecosystems. And they are created from the interaction of rock, water, air, and living organisms. Microbes and plant roots break down minerals and create complex organic compounds that store nutrients and water. Soils develop slowly, often taking thousands of years to form a few centimeters. They can be destroyed much faster by erosion, making them one of Earth's most vulnerable resources. Earth's polar regions play a special role in regulating climate. Ice sheets and sea ice reflect sunlight and cool the planet, while also storing large amounts of fresh water. When ice melts, it raises sea level and reduces reflectivity, leading to further warming. Ice cores drilled from glaciers preserve detailed records of past climates, trapping bubbles of ancient air that reveal the composition of the atmosphere thousands of years ago. The deep ocean, although dark and cold, is one of the largest habitats on Earth. Life there relies not on sunlight, but on chemical energy from reactions involving sulfur, methane, and other compounds. These ecosystems show that life can exist under conditions very different from those on the surface, expanding our understanding of where life might exist on other planets. Human activity has become a significant force in Earth's systems. Agriculture, industry, urbanization, and energy production have altered land surfaces, changed river flows, modified the composition of the atmosphere, and influenced climate. Humans now move more sediment each year through construction and mining than all natural rivers combined. This makes humanity a geological agent, capable of reshaping the planet on a global scale. This influence brings both risk and responsibility. The interconnected nature of Earth's systems means that actions in one place can have consequences far away and far into the future. Emissions released today can affect climate for centuries. Land use changes can alter water cycles and biodiversity for generations. Understanding Earth as an integrated system is therefore essential for making informed choices about how to live on it. Beyond the visible surface and the familiar rhythms of weather and seasons, Earth operates through a series of slow chemical and physical exchanges that link rocks, water, air, and life into a single evolving system. These exchanges are often called biogeochemical cycles, and they control the availability of essential elements such as carbon, nitrogen, oxygen, phosphorus, and sulfur. Without these cycles, life could not be sustained over long periods. Carbon, for example, moves through the atmosphere, oceans, soils, living organisms, and rocks. Plants take carbon dioxide from the air and use it to build their tissues. Animals eat plants and incorporate carbon into their own bodies. When organisms die, their carbon is returned to the environment through decay. Some of it becomes buried in sediments and eventually forms coal, oil, or limestone. Over millions of years, tectonic processes bring these materials back to the surface, where weathering and volcanic activity release carbon again. This long loop links the living world to the deep earth. Nitrogen follows a similarly complex path. Although nitrogen gas makes up most of the atmosphere, most organisms cannot use it directly. Specialized bacteria convert nitrogen gas into forms that plants can absorb. Other bacteria return nitrogen to the atmosphere through different chemical reactions. This microbial mediation makes nitrogen available to the entire food web and shows how microscopic life controls planetary scale processes. The chemistry of Earth's oceans and atmosphere is also shaped by reactions that occur on mineral surfaces. When rainwater reacts with rocks, it consumes carbon dioxide and produces dissolved ions that are carried to the sea. There, some of these ions are used by marine organisms to build shells and skeletons. When these organisms die, their shells sink and become part of the seafloor. Over time, this process removes carbon from the atmosphere and stores it in rocks, acting as a long-term climate regulator. Earth's crust itself is chemically diverse, reflecting its long and complex history. Different regions contain different combinations of minerals shaped by past volcanic activity, mountain building, and erosion. This diversity influences soil fertility, water chemistry, and the types of ecosystems that can develop in different places. Tropical soils, for example, are often deeply weathered and low in nutrients, while soils formed from volcanic ash can be extremely fertile. The atmosphere is not chemically uniform either. It contains trace gases such as methane, ozone, and nitrous oxide that have strong effects on climate and chemistry, despite their low concentrations. These gases are produced and consumed by both natural processes and human activities. Small changes in their abundance can have large effects on Earth's energy balance and environmental conditions. Earth's upper atmosphere interacts directly with space. Solar radiation ionizes atoms and molecules, creating charged particles that form layers such as the ionosphere. These layers influence radio communication and respond to changes in solar activity. During solar storms, increased radiation can heat the upper atmosphere, cause it to expand, and affect satellites and communication systems. This shows that Earth's environment extends far beyond the surface and is connected to processes in the sun. The planet's long-term stability is not the result of any single mechanism, but of the interaction among many feedbacks. When temperatures rise, weathering rates increase, removing more carbon dioxide from the atmosphere and reducing warming. When temperatures fall, weathering slows, allowing carbon dioxide to accumulate and warm the planet. This negative feedback helps prevent extreme climates over geological time. However, this regulation operates slowly and can be overwhelmed by rapid changes. Extinction and evolution are also part of Earth's system. Mass extinctions remove large fractions of life, but they are followed by periods of rapid evolution as surviving species adapt and diversify. These events reshape ecosystems and alter the flow of energy and matter through the biosphere. In this way, biological history becomes part of geological history. Earth's surface preserves a record of these changes in rocks, fossils, and landforms. Sedimentary layers record past environments. Volcanic rocks record episodes of intense activity, and fossils record the history of life. By studying these records, scientists reconstruct the story of Earth and identify patterns that help predict future changes. The concept of Earth as a system emphasizes that no part of the planet can be fully understood in isolation. Climate cannot be understood without oceans. Oceans cannot be understood without chemistry. Chemistry cannot be understood without life, and life cannot be understood without geology. The planet is a network of interacting processes that operate on different timescales, but influence one another continuously. Human society has emerged within this system and now influences it in significant ways. Our technologies alter chemical cycles, our land use reshapes ecosystems, and our energy choices affect climate. We are therefore not separate observers of Earth, but active participants in its ongoing evolution. Recognizing this connection changes how we understand our place in the world. It suggests that environmental challenges are not external problems, but changes within the system that supports us. Solutions must therefore consider the whole system rather than isolated parts. Sustainable interaction with Earth means aligning human activities with the natural cycles and limits that have governed the planet for billions of years. The future of the Earth will be shaped by both natural processes and human decisions. On geological timescales, continents will continue to drift, oceans will open and close, and mountains will rise and erode. These slow processes will reshape the surface again and again, just as they have throughout the planet's history. New supercontinents will form, new ocean basins will appear, and climates will change as land and sea are rearranged. The sun will also change. Over billions of years, it will become brighter and hotter as it ages. This gradual increase in solar energy will eventually make Earth's surface too warm for liquid water to exist, ending the conditions that support life as we know it. Long before this happens, however, Earth will pass through many intermediate states shaped by climate feedbacks, biological evolution, and tectonic change. Life itself will continue to evolve in response to changing conditions. Species will adapt, migrate, or disappear. New forms of life may arise, filling ecological roles that do not yet exist. The biosphere will remain dynamic, continually reshaping itself in response to both internal and external influences. Human civilization is now one of the strongest forces acting on Earth's systems. Our use of energy, land, water, and minerals affects climate, biodiversity, and chemical cycles. This influence can either destabilize or help stabilize the planet's systems, depending on how it is managed. Technologies that reduce emissions, protect ecosystems, and recycle resources can reduce pressure on natural systems and help maintain conditions favorable to life. Understanding Earth as a system encourages long-term thinking. It highlights that actions taken today can have effects that last far beyond a human lifetime. Carbon released now may remain in the atmosphere for centuries. Species lost today will not return. Landscapes altered today may take millennia to recover. This perspective shifts the focus from short-term gains to long-term stability. Earth science also provides a sense of perspective. Human history occupies only a tiny fraction of Earth's timeline, yet human actions now rival natural forces in their impact. This combination of small temporal scale and large influence is unique and places a special responsibility on our species. The planet's past shows that change is inevitable, but it also shows that certain conditions have allowed life to flourish for long periods. Stable temperatures, liquid water, moderate atmospheric composition, and active geological recycling have together created a habitable world. Preserving these conditions is not about freezing the planet in one state, but about avoiding changes that push it beyond its natural range of variability. The story of Earth is therefore not only a scientific narrative, but also a guide for decision-making. It teaches that systems are interconnected, that feedbacks can amplify or reduce change, and that resilience depends on diversity and balance. These lessons apply not only to ecosystems and climate, but also to human societies. In this sense, studying Earth is not just an academic exercise. It is a way of understanding the context in which humanity exists and the limits within which it must operate. The planet is both our home and our life support system. Protecting its stability is not a matter of preference, but of necessity. Earth will continue its journey through space long after current civilizations have changed or disappeared. Mountains will rise and fall, oceans will shift, and life will adapt in ways we cannot predict. But the choices made in the present will influence how this future unfolds, at least for the next few centuries and millennia. The Earth is not a static object, but an ongoing process. It is a planet that becomes something new in every moment, shaped by forces that range from the movement of atoms to the motion of continents and the evolution of life. Understanding this process gives meaning to our place in the universe and reminds us that we are part of a much larger story. The Earth is often imagined as a stable, solid sphere moving quietly around the sun, yet this image hides the immense complexity and activity that define the planet. From its deepest interior to the edge of its atmosphere, Earth is a dynamic system driven by energy flows, chemical exchanges, and physical motion. Every part of the planet is connected to every other part, and even the smallest changes can have consequences that unfold over long periods. Beneath the crust lies the mantle, a vast region of hot, slowly moving rock. This movement is driven by heat escaping from the core and from radioactive decay. Although mantle flow is extremely slow, it is powerful enough to move continents, create mountains, open oceans, and trigger volcanic eruptions. The surface geography of Earth is therefore temporary, shaped and reshaped by forces that operate beyond human timescales. Earth's core is divided into a solid inner core and a liquid outer core. The movement of liquid iron in the outer core generates Earth's magnetic field. This magnetic field extends far into space and forms a protective region that shields the atmosphere and surface from much of the harmful radiation and charged particles coming from the sun. Without this field, Earth might have lost much of its atmosphere, making the surface far less hospitable to life. The planet's rotation affects almost every surface process. Rotation causes day and night, drives atmospheric circulation through the Coriolis effect, and influences ocean currents. It also shapes Earth's geometry, causing a slight bulge at the equator. Over long periods, rotation slows due to tidal friction with the moon, slowly changing the length of the day. Earth is not isolated from space. It constantly interacts with solar radiation, cosmic particles, and gravitational forces from other celestial bodies. Variations in Earth's orbit and axial tilt change how sunlight is distributed across the planet, influencing long-term climate cycles. Solar storms can temporarily disturb Earth's magnetic field and upper atmosphere, affecting satellites and communication systems. The atmosphere itself is layered and structured. Each layer has different properties and plays a different role in protecting and regulating the planet. The atmosphere filters harmful radiation, transports heat and moisture, and supports chemical reactions that shape climate and air quality. Tiny particles suspended in the air influence cloud formation, rainfall, and how much sunlight is reflected or absorbed. Water exists on Earth in many hidden and visible forms. Beyond oceans and rivers, large amounts of water are stored underground and within minerals deep in the mantle. This water influences rock behavior, volcanic activity, and tectonic motion. The exchange of water between surface and interior is slow but continuous, linking geological and hydrological processes. Life has become a major force in shaping Earth. Through photosynthesis, respiration, decay, and the formation of shells and reefs, organisms modify the atmosphere, oceans, and land. Over billions of years, life transformed Earth's chemistry and surface, making it a planet whose physical state is inseparable from its biological history. The oceans regulate climate by absorbing and redistributing heat and carbon dioxide. Currents connect distant regions, linking polar ice to tropical warmth. Changes in ocean circulation have driven major climate shifts in the past and will continue to do so in the future. Earth's climate emerges from the interaction of solar energy, atmospheric composition, ocean circulation, ice coverage, and biological activity. Feedback loops within this system can amplify or reduce changes, leading to periods of relative stability or rapid transition. Understanding these feedbacks is key to understanding Earth's past and future. Earth is therefore not a static object, but a continuously evolving system. It is a planet in motion, shaped by forces that range from the atomic to the planetary scale. Studying Earth means studying change itself and recognizing that the world we inhabit is the temporary result of processes that began long before humans existed and will continue long after. The planet's surface is continuously reshaped by the combined action of tectonics, erosion, and biological activity. Mountains rise when plates collide, but they begin to erode almost immediately under the influence of wind, water, and ice. Rivers carry the products of erosion toward the oceans, where they settle as sediments on the seafloor. Over time, these sediments become rocks that may later be uplifted again, closing a slow geological loop. This constant recycling means that Earth's surface has very little that is truly permanent. Even the oldest visible rocks are only a small fraction of the planet's age. Most of Earth's early crust has been destroyed and recreated many times. The planet therefore preserves its history not in single locations, but in patterns distributed across the globe. Climate plays a central role in shaping landscapes. In wet regions, chemical weathering dissolves minerals and forms deep soils. In dry regions, physical weathering breaks rocks into fragments that are transported by wind. In cold regions, ice wedges and glaciers fracture rock and carve valleys. Each climate zone leaves its own signature on the land. The atmosphere acts as a global transport system, moving heat, moisture, dust, and gases around the planet. Winds carry desert dust across oceans, fertilizing distant ecosystems. Volcanic ash can travel around the globe and influence climate for years after an eruption. Pollutants released in one region can affect air quality in ecosystems thousands of kilometers away. The oceans are also active transport systems. Surface currents driven by winds and deep currents driven by density differences form a global circulation that moves heat, salt, and nutrients around the planet. This circulation influences where storms form, where rain falls, and where life can thrive. Earth's polar regions play a disproportionate role in regulating global climate. Ice reflects sunlight, cooling the planet, while melting ice reduces reflectivity and accelerates warming. The formation and melting of ice also affect sea level and ocean circulation, linking polar processes to conditions far from the poles. The biosphere responds to environmental change, but also modifies it. Forests influence rainfall by releasing moisture into the air. Plankton in the oceans influence cloud formation by releasing particles that seed clouds. Even microorganisms in soils affect how quickly organic matter decomposes and how much carbon is stored underground. Over long periods, life and environment co-evolve. Changes in climate drive evolutionary adaptation, while evolutionary changes alter ecosystems and environmental processes. The rise of flowering plants, for example, changed soils, atmospheric composition, and animal evolution all at once. Earth's system is therefore not simply physical or biological, but both at once. Geology sets the stage, climate sets the conditions, and life fills the space and modifies the rules. This integration makes Earth unique among the planets we know. Human societies have become deeply entangled with these systems. Agriculture depends on climate, soils, and water cycles. Cities depend on stable coastlines, predictable weather, and reliable resources. As societies grow and change, they alter the very systems they depend on. This creates a feedback between human activity and Earth's natural processes. Understanding this feedback is essential for managing future change. Without such understanding, actions meant to improve human well-being may unintentionally destabilize the systems that support it. Earth's complexity does not imply fragility alone, but also resilience. The planet has passed through ice ages, mass extinctions, and periods of intense volcanism, yet life has persisted. However, resilience has limits, and extreme or rapid changes can push systems beyond their capacity to adapt. The challenge for humanity is to recognize these limits and act within them. This requires seeing Earth not as a resource to be used without consequence, but as a system to be understood and respected. Beyond the familiar patterns of land, sea, and sky lies a set of processes that are almost invisible but deeply important. One of these is Earth's slow chemical evolution. Over time, the composition of rocks, oceans, and the atmosphere changes as elements move between different forms and locations. This chemical motion is as important as physical motion in shaping the planet. Weathering is a key part of this chemical evolution. When rainwater interacts with rocks, it dissolves minerals and alters their structure. This process consumes carbon dioxide and produces dissolved ions that rivers carry to the sea. In the ocean, these ions can be used by organisms to build shells or can settle as sediments. Over millions of years, this removes carbon from the atmosphere and stores it in rocks, helping regulate climate. Another invisible process is the slow diffusion of heat through Earth's interior. Heat moves from the core toward the surface, not only by convection in the mantle, but also by conduction through solid rock. This slow leakage of heat powers geysers, hot springs, and the slow deformation of the crust. Earth's upper atmosphere is shaped by interactions with solar radiation. Ultraviolet light breaks apart molecules, creating reactive species that participate in atmospheric chemistry. This chemistry controls ozone levels, influences climate, and affects the transmission of radiation to the surface. The planet's orbit around the sun is not perfectly stable, but changes slightly over time due to gravitational interactions with other planets. These variations influence the timing and intensity of seasons and are linked to long-term climate cycles, such as ice ages. Earth's history includes periods when the planet was much warmer or much colder than today. These past climates show that Earth can exist in very different states, and that transitions between these states can be abrupt or gradual, depending on the balance of forces involved. The fossil record reveals that life has repeatedly adapted to these changes, sometimes through slow evolution and sometimes through rapid diversification after mass extinctions. This history shows that stability is not the norm, but a temporary condition within a broader pattern of change. The deep ocean holds clues to Earth's past climates in its sediments and chemical composition. Layers of sediment preserve records of temperature, biological productivity, and ocean chemistry that extend back millions of years. By studying these layers, scientists reconstruct the planet's environmental history. Earth's magnetic field has also changed over time. It has reversed polarity many times, with north and south swapping places. These reversals are recorded in magnetic minerals and rocks and provide a timeline for geological processes. The surface of Earth preserves traces of ancient environments in its rocks and landforms. Desert sandstones, tropical limestones, and glacial deposits all record climates very different from today's. These records show that Earth's present state is only one moment in a long sequence. Human understanding of Earth has grown rapidly in recent centuries, but it remains incomplete. Many regions of the deep ocean, the deep crust, and the upper atmosphere remain poorly explored. New technologies continue to reveal previously unknown aspects of the planet. As knowledge grows, so does the realization that Earth's systems are tightly linked and sensitive to change. This awareness has transformed Earth science from the study of separate disciplines into the study of an integrated system. The Earth is therefore best understood not as a collection of parts, but as a whole whose behavior emerges from the interaction of many processes operating at different scales. Earth's surface environment is shaped not only by natural forces, but also by the long-term accumulation of small changes. Over thousands of years, rivers shift their paths, coastlines advance or retreat, and forests expand or shrink. These changes rarely attract attention individually, but together they transform entire regions. Coastlines are especially dynamic. Waves erode cliffs, currents transport sand, and rising or falling sea levels change the shape of shores. Barrier islands migrate, deltas grow or collapse, and coral reefs build massive limestone structures that alter ocean currents and protect coastlines from storms. Earth's hydrological system connects atmosphere, land, and ocean into a single loop. Water evaporates from oceans, falls as rain on land, flows through rivers, and returns to the sea. Along the way, it dissolves minerals, transports nutrients, and supports ecosystems. This continuous motion links climate to geology and biology. Freshwater is a limited resource on Earth. Although the planet contains vast amounts of water, only a small fraction is available as fresh, accessible water for ecosystems and human use. This makes the management of rivers, lakes, and aquifers a critical aspect of sustainability. Earth's soils are another thin but essential layer. They support nearly all terrestrial life and agriculture, yet they form slowly and can be lost quickly through erosion. Soil health depends on the balance of minerals, organic matter, microorganisms, and water. Disrupting this balance can lead to land degradation and reduced productivity. The biosphere is not evenly distributed across the planet. Tropical regions contain far more species than polar regions, and oceans contain far more biomass near coastlines than in the open sea. This uneven distribution reflects differences in energy availability, nutrient supply, and environmental stability. Energy from the sun is the ultimate driver of most surface processes, but energy also flows from Earth's interior. These two energy sources interact to create complex patterns of motion and change. Solar energy drives climate and life, while internal energy drives tectonics and volcanism. The long-term interaction between internal and external energy has produced a planet that is both geologically active and biologically rich. This combination appears to be rare among known planets and may be one reason Earth supports such complex life. Earth's environment is therefore the product of both chance and necessity. Chance events such as asteroid impacts and volcanic eruptions have altered the planet's course, while necessary processes such as gravity, thermodynamics, and chemistry have guided its overall evolution. Understanding Earth requires accepting this mixture of predictability and unpredictability. Some changes follow regular cycles, while others occur suddenly and unexpectedly. Both types of change have shaped the planet's history. Human civilization now operates within this dynamic context. Our cities, farms, and technologies depend on stable environmental conditions, yet they also influence those conditions. This creates a need for careful management and long-term planning. Earth's future will be shaped by how well human societies integrate their activities with the planet's natural systems. This integration requires knowledge, cooperation, and a willingness to consider consequences beyond immediate benefit. The study of Earth therefore becomes not only a scientific pursuit, but also a guide for living responsibly on a complex and changing planet. Earth's ecosystems form complex networks in which energy and matter flow through many pathways. Plants capture solar energy and convert it into chemical energy, which is then transferred through food webs. Predators, decomposers, and microorganisms all play roles in recycling nutrients and maintaining balance. Disruptions to one part of this network can spread through the entire system. Biodiversity increases the resilience of ecosystems. When many species perform similar functions, the loss of one species may be compensated by others. When diversity is low, ecosystems are more vulnerable to collapse. This principle applies not only to forests and reefs, but also to agricultural systems and human-managed landscapes. The deep biosphere extends far below the surface into rocks and sediments kilometers underground. Microorganisms live in these environments without sunlight, using chemical energy from rocks and fluids. This hidden biosphere contains a large fraction of Earth's total biomass and influences geochemical cycles. Evolution is shaped by both environmental change and internal biological processes. Genetic variation, mutation, and natural selection allow populations to adapt to changing conditions. Over long timescales, this process produces new species and new ecological relationships. Earth's history includes long periods of relative stability, punctuated by episodes of rapid change. These transitions often coincide with shifts in climate, tectonics, or chemistry. Understanding these patterns helps scientists assess the risks and consequences of current changes. The planet's climate system contains both stabilizing and destabilizing feedbacks. Stabilizing feedbacks dampen change, while destabilizing feedbacks amplify it. The balance between these feedbacks determines whether the climate remains stable or shifts to a new state. Human activity has added new feedbacks to the system. The release of greenhouse gases warms the planet, which can trigger further warming through melting ice and changes in vegetation. At the same time, human efforts to restore ecosystems or reduce emissions can create stabilizing feedbacks. The interaction between natural and human-driven processes is now one of the defining features of Earth's system. This interaction creates new challenges and opportunities for managing the planet. Earth's long-term habitability depends on maintaining conditions within a certain range. Extreme temperatures, loss of water, or major chemical imbalances could make the planet less supportive of life. The responsibility for maintaining these conditions increasingly lies with humanity. This responsibility is shared across nations, cultures, and generations. Understanding Earth is therefore not only a matter of curiosity, but of survival. The more we understand the planet's systems, the better we can align human activities with them. Human culture, technology, and knowledge have become intertwined with Earth's physical systems in ways that no previous species has achieved. Cities modify local climates through heat retention, altered wind patterns, and changes in surface reflectivity. Large reservoirs change river flows, sediment transport, and regional weather. Transportation networks move organisms, minerals, and chemicals across the globe, connecting ecosystems that were once isolated. This connectivity has created a truly planetary-scale society, but it has also created planetary-scale consequences. Species that evolve in one region can spread rapidly to others, sometimes becoming invasive and disrupting local ecosystems. Pollutants released into air or water can travel far beyond their source, affecting environments and communities that did not produce them. At the same time, global communication and scientific collaboration allow humanity to observe Earth in unprecedented detail. Satellites monitor forests, ice sheets, ocean temperatures, and atmospheric composition continuously. This global view reveals patterns that are invisible from the ground, such as large-scale deforestation, shifting climate zones, and changes in ocean circulation. Earth observation has transformed our understanding of the planet from a collection of local environments into a single interconnected system. It has shown that environmental change is rarely isolated, and that solutions must therefore be coordinated across regions and nations. Technological development also changes how humans interact with Earth's resources. Renewable energy reduces dependence on fossil fuels, but requires minerals for batteries, solar panels, and wind turbines. Agriculture becomes more efficient, but also more intensive, placing pressure on soils, water, and biodiversity. Each technological advance brings both benefits and new challenges. The concept of sustainability emerges from this recognition. Sustainability is not simply about reducing harm, but about designing systems that can operate indefinitely within Earth's limits. This requires balancing resource use with regeneration, emissions with absorption, and development with conservation. Cultural values influence how societies define and pursue sustainability. Some cultures emphasize harmony with nature, while others emphasize control and exploitation. These values shape policies, technologies, and behaviors, influencing Earth's future as much as physical laws do. Education plays a crucial role in shaping these values. Understanding Earth science helps people see the connections between actions and consequences, between local behavior and global impact. This understanding can motivate more responsible choices and support collective action. The story of Earth is therefore not only written in rocks and fossils, but also in ideas, institutions, and decisions. Human history has become part of Earth history, and the two can no longer be separated. This integration does not mean that humans dominate Earth, but that we are deeply embedded within it. Our survival depends on the stability of climate, the fertility of soils, the purity of water, and the diversity of life. These are not external goods, but the foundations of civilization. Recognizing this dependence shifts the perspective from one of ownership to one of stewardship. Earth is not a possession, but a process, and humanity is one participant in that process. The future of Earth will therefore be shaped not only by tectonics and solar evolution, but also by human choices. Whether the planet remains hospitable for complex life depends on how well these choices align with the planet's natural systems. Earth's long-term future extends far beyond the time horizon of human civilization. On timescales of tens to hundreds of millions of years, continents will merge into new supercontinents, ocean basins will open and close, and climate will shift as land and sea are rearranged. These changes will reshape atmospheric circulation, ocean currents, and ecosystems in ways that are difficult to predict, but inevitable in principle. The sun's gradual brightening will slowly increase the amount of energy Earth receives. This will intensify weathering, increase evaporation, and eventually destabilize the climate system. Long before Earth becomes uninhabitable, however, it will pass through many transitional stages with climates and ecosystems very different from those of today. Life will respond to these changes through evolution, migration, and adaptation. Some species will go extinct, others will diversify, and new forms of life may emerge. The biosphere will continue to be dynamic, reshaping itself in response to both internal and external forces. Human civilization may not persist long enough to witness most of these changes, but its actions in the present can influence near-term trajectories that affect many future generations. This gives present-day societies a unique position in Earth's history, the ability to influence planetary conditions intentionally. The ethical implications of this influence are profound. Decisions about energy, land use, and resource management shape not only current well-being, but also the environmental conditions inherited by future generations and other species. Earth science provides tools for understanding these consequences, but it does not dictate values. Values come from culture, philosophy, and social negotiation. Integrating scientific understanding with ethical reflection is therefore essential for responsible decision-making. The concept of planetary boundaries reflects this integration. It identifies limits within which human activity can occur without destabilizing Earth's systems. Crossing these boundaries risks triggering large-scale, potentially irreversible changes. These boundaries are not fixed lines, but zones of increasing risk. They depend on scientific knowledge that evolves over time and on societal judgments about acceptable risk. The recognition of Earth as a shared home has led to new forms of international cooperation focused on climate, biodiversity, and sustainable development. These efforts reflect an emerging awareness that many challenges transcend national borders and require collective solutions. Whether these efforts succeed will shape the planet's near future. The outcome is uncertain, but the existence of such cooperation shows that humanity is capable of responding collectively to global challenges. Earth's story thus continues to unfold, shaped by the interaction of natural processes and human choices. It is a story without a final chapter, only ongoing change. Understanding this story does not provide certainty, but it provides context. It places human existence within a vast continuum of planetary evolution and reminds us that our actions are part of that continuum. The idea of Earth as a living planet has evolved over time from metaphor to scientific framework. While Earth is not alive in a biological sense, its systems exhibit behaviors that resemble living processes: self-regulation, feedback, adaptation, and resilience. These properties emerge from the interaction of physical, chemical, and biological components. The concept of resilience is particularly important. A resilient system can absorb disturbances and reorganize while retaining its basic structure and function. Forests recover after fires, coral reefs can regenerate after storms, and climates can stabilize after periods of disruption. However, resilience is not infinite. Repeated or extreme disturbances can push systems beyond their capacity to recover. Earth's history contains many examples of both resilience and collapse. After mass extinctions, life rebounded in new forms, but the recovery often took millions of years. After major climate shifts, ecosystems reorganized, sometimes with entirely different dominant species. These patterns show that recovery is possible but slow, and that losses can be permanent on human timescales. Human societies are part of this pattern. Civilizations have risen and fallen in response to environmental change, resource availability, and social dynamics. The scale is different, but the principle is the same. Systems persist when they can adapt and reorganize. Modern society has unprecedented capacity to alter its environment, but also unprecedented capacity to understand and manage those alterations. Science, technology, and communication provide tools for monitoring Earth and for coordinating responses to change. Whether these tools are used wisely remains a central question. The future of Earth will not be determined by a single event or decision, but by the accumulation of many small actions over time. Policies, technologies, cultural shifts, and individual behaviors all contribute to the trajectory of change. This makes the future both uncertain and open to influence. Seeing Earth as a system encourages humility. It reminds us that no single group or species controls the planet, and that unintended consequences are always possible. It also encourages responsibility, because awareness creates obligation. Earth's long story continues, written in the motion of plates, the flow of rivers, the growth of forests, and the evolution of life. Humanity has become a new chapter in that story, capable of altering its course, but also dependent on its continuity. The ultimate lesson of Earth science may be that change is inevitable, but direction is not. The planet will continue to evolve, but the conditions under which future generations live depend in part on choices made today. Understanding Earth, therefore, is not only about knowing how the planet works, but about knowing how to live within it. It is about recognizing limits, valuing diversity, and maintaining the balance that allows complex life to flourish. Earth is not merely the stage on which human history unfolds. It is an active participant in that history, shaping and being shaped by the actions of all living things. This perspective transforms Earth from an object of study into a partner in existence, a dynamic, evolving system whose future is intertwined with our own.